Uh-oh, looks like Megyn Kelly has a follow-up. So recall we were talking about Donald Trump throwing a small rock at a basket of kittens, 5 meters per second, 45 degrees. And there was some discussion about the circular motion at the apex. Now, Megyn wants to know, what are the radial and tangential acceleration components 3/4 through the path? So at that point, it is not circular motion. That's about what we drew here. Not circular motion, but for any path, you can define radial and tangential acceleration. It's just the acceleration component perpendicular to the curve and along the curve. So we just have to see how to get that for a simple trajectory problem. All right, well, first of all, 3/4 through the path, that could mean space or time. It actually doesn't matter which one you think about, because the velocity is constant in the x, you could either solve it either way. But let's solve it for time. 75% through the path would be 75% of what we called before the hang time. Right, so you may remember that the hang time was 2 times v naught sine theta over g. And that's really just saying, what is this vertical component? It's got to go all the way to 0 and then back to its value again. How long does it take that to happen based on this acceleration? It's really just the velocity over acceleration. And you double it because it has to go up and down. So all we're going to do now is put 0.75 in front of it to get 0.75 of the hang time. All right. So that's going to be 0.75 times 2, and then v naught sine, let's see, 5 times the sine of 45, I just worked out, it's 3.54 meters per second. And we're going to put that over 9.8. To get this time that we're looking for is 0.54 seconds. So this, and I guess that's about right there, occurs at 0.54 seconds. Now what we got to do is figure out what are the components of the acceleration, which the whole time is just gravity straight down. Our total acceleration is 9.8 down. We have to get it in components along the path. So let's think about that for a minute. Along the path, so if we zoom in on the path here, like that, and say this is the point in time, you may recall that the direction of the path is the same as the direction of the velocity vector, because velocity is always proportional to the displacement. It's what's the displacement direction is the direction. So if we wanted to think about the direction of the path tangential, it looks something like that. And if you want that, you got to think about the x and y components of velocity to get it. So let's take this and write, let's write real quick. How would we write the velocity vector? The velocity would be the x component, which is 3.54. Sine and cosine of 45 are the same. So 3.54 meters per second I hat. And then the y component of the velocity would be 3.54 is the initial. And it's, of course, decelerating, so minus gt, minus 9.8 t. That's the j hat component. So if we wanted to get it right at a certain time, all we got to do is plug in 0.54 seconds right there in that minus 9.8, and we're going to get that the velocity vector at 0.54 is going to be 3.54 I hat, that one's constant, minus, it comes out negative 1.77 j hat. And that makes sense. You would expect that as it starts with a positive velocity, y velocity, the component should be negative as you come this way. So to get the angle, you may recall that it's the tangent of theta is the y component over the x component. And so you may remember that it looks like this. Tangent theta is vy over vx, which in this case, 1.77 over 3.54 turns out to be a half. Right? Take the inverse tangent of that. I'm sorry, not a half. Inverse tangent of that, in the end, you'll get minus 27 degrees. So I didn't actually work out this number for you. I'll say it's like that. It's minus 1.77 over 3.54. Yeah, it is a half. Yeah, so theta comes out to be minus 27 degrees. Minus 27 degrees. What you got to remember is that angle is assuming the proper definition of theta. Remember, so theta always starts from the horizontal axis to the right and goes this way. So minus 27 degrees, they're really telling you that angle. It's below the normal. So there's the direction of the path. All we got to do now is get the acceleration due to gravity broken into components along the path. That's AT, and perpendicular to the path. That's the radial. There they are right there, and here's your right triangle. 90 degrees always between the two components. And now we just got to figure out if that's 27 degrees and this is 90 degrees because it's y and the horizontal, then what is this? And it must be therefore 63 degrees. So we'll do a little bit of trig there, and we'll find then that the component along the tangential looks like it must be, if that's 63, it looks like it must be 9.8 times the cosine of 63. So A tangential is 9.8 cosine 63 degrees, and the tangential component is, I get 4.45 meters per second squared. So there's AT, and the radial component, A radial, is this one. It looks like it must be 9.8 times sine, opposite over hypotenuse, so katoa all the time, sine of 63. But we need a negative sign, because usually if you have something curving like this, you define the radial unit vector as out. Since it's curved this way, the radius, if you think of that as a circle, radius is out. And here we're pointing in, so I'm going to stick a negative sign on it. And I got minus 8.73. 8.73 meters per second squared. So AR minus 8.73. Does that all make sense? Yeah, pretty much. G, if we're thinking of in terms of this, it's going to have some component along the path, 3/4 of the way through, but still a bigger component perpendicular to the path, or some other component in the path. So it looks like it makes sense, and the numbers work out.